of data and task parallelism. So when I say data parallelism, I have multiple processes and lot of data, and the data is divided into packages or groups, and different packages of data are given to different processes, and all the processes do the same computation. That is data. This is more common, and it generally all supercomputers, this is what is happening. Like if you take weather forecasting, so much of data is there. So maybe the algorithms to predict are not so complicated, but the data is massive. It is a big data problem. So you need multiple processors to do the same operation on packages of data. And this is most supercomputers have this, use this. High performance computers generally use this only. Now, task parallelism is a different thing. You have every processor do a different task, and in that process you divide the work in such a way that the tasks are in parallel. It is quite likely that some processors may not have a lot of work to do, some may have. I told you the example of making a Onam Sadhya, same thing. I also told you about a parallel algorithm where you are writing the algorithm itself in parallel, or you are converting an algorithm into a normal algorithm, say a Dijkstra's shortest path first algorithm. You are dividing it into a parallel process. So that is parallelizing a serial algorithm, which is more common. And what we do is we break the problem, we identify the algorithm into threads or packages, and divide it into different threads and give it to each processes. That is a general thing in decomposition, and so on. Then I also told you that when we are having parallel processes, parallel systems, definitely we are not going to have a total division of time. If you have, say, if one processor is doing the job in 10 minutes, you have 5 processors, it will not happen in 2 minutes. 10 divided by 5 does not work out. It never will happen. It may be 4 or 5 minutes. Because some problems there could be a good output, like a Monte Carlo simulation is like that, but mostly you will not get that kind of output, because that is called throughput. That throughput may not happen because throughput will be there, latency will also be there. Latency is delay, throughput is maximum output, because there is some loss will be there. There is some overhead which will be there when we are having parallel computation, because the processors need some global variables. Processors are sharing the memory, storage. The processors have to talk to each other. They have to communicate with each other. They have to collaborate with each other. They need some global variables, only then they can do the job. So they have to wait for some global variables. The global variables have to be given to all the processes, only then, or each processor needs the global variable to start work. So these are the sources of overhead. And one more way that you can have overhead is contention. One processor is, the action of one processor is interfering with another processor. Both of them are accessing the same resource. It could happen. And both are accessing the same bus. Both are got into some deadlock condition. All these will result in performance loss. So for that, the best way is going for multi-threading. Threads are very, very advantageous. I have already told you that a program consists of many processes. A process is nothing but a program in execution, and a process can be divided into threads. Threads are lightweight, agile, easy to easy to create, easy to kill, easy to tear down, very dynamic. They have only one address space, not much of memory swap happens. And processes, on the other hand, are slightly complicated. So today we will be seeing this process versus thread. And I already told you that normally most of these high performance computers or parallel computers or supercomputers generally have access to a shared memory architecture. 99% it is like that. And because of that, you need to have processes and threads. Threads a process is basically a part of a program. A process has its own private address space. Process do not communicate through shared memory, but need another mechanism like message passing, which we have seen in the earlier course, and so on. So the best way is divide this process into smaller threads. A thread is lightweight, easy to create, easy to kill. A thread can have shared access to memory, unlike a process. Process needs to have a message passing interface, a send and receive primitive. Here it's not needed. There is a shared access. There are global variables. There are some local variables. There is a stack. It's a very easy way to do things. And that is why a thread is very lightweight, and it's ideal that we divide a process into threads T1, T2, T3, T4, and the threads share code, data, and kernel context. Now, threads can be concurrent or sequential. If you see A, first second the thread is there, second it is idle, third second it is idle, fourth second it is again coming, right? So these kind of things happen. A and B are A and C are concurrent. They are concurrently happening, right? At the same time something is happening. There can also be sequential threads. If you see the diagram, A and B are concurrent, A and C are concurrent, and B and C are sequential. Say different time instance. B is happening in a totally different time instance. There is no sharing. On the other hand, C is happening in a total. B and C are completely sequential, different time instances. Here, A is repeating in different time instances. So that is why it is a concurrent application. Now, the advantage of thread is very simple. We can have threads going to a separate processor. One core or one processor can have all the threads. You can send one thread to here. You can have T1 or T3, T5 go all to core 1. You can have T2, T4, T2, T4 into another. So obviously when you have threads, there is a parallel execution, there is a parallel processing, and as a result it is faster, it is resource sharing, it is easier, it is scalable. You can easily scale it up so that the threads can be given to different processes. It is parallelizing, it is responsive, it is sharing of resources, economical, and so on. But of course, one issue is there will be that every thread we needs access to some global variables or shared variables, like static variables, blocks, and heap. But at the same time, the thread will have its own local or private variables. So that we should understand. The thread is lightweight, simple, easy to open, easy to kill, easy to use, very easily parallelizable. But the thread has to have its own local variable and needs access to global variables, and so on. So there are different threads that we use. Thread libraries are there. PT threads is one library primarily used in Solaris and Unix. It is a good thing, and there is OpenMP is another standard for threads. P4 Permax is another thing. I believe OpenMP is used in, I think it is used in what is that, several scientific programming applications, and so on and so forth. So in the subsequent classes we will see PT threads. I'll try to get some video lecture on PT threads, and we will also see some, that we have already seen these things, in operating system, a critical section, synchronization using a mutex lock, using a semaphore, a conditional variable. Those things are applicable here also when we come to threads. I won't go into much detail in all these things because we have already seen these in the earlier course. So that's all for today. We will meet on. We're not going to meet on Monday. Monday we will have your last quiz. So I'm going to give you a heads up on the midterm. As I mentioned, for a change, I will tell you the syllabus, the questions for the midterm. The midterm will be half of you will be doing a problem Ricard Agarwala, and half of you will be doing Meikawa's algorithm. So what you will have to do is, in that you have to probably work ahead of schedule, and during the exam you would be submitting that program, that kind of a simulation you can do and give it. So you can start preparing now itself, writing the Meikawa's, and I will have some software that will check for plagiarism also. So please start working on it. In another 3-4 classes the syllabus will be over, so perhaps by September 10th we will be having no more classes, and your exam will be probably in the first week of October or something, September 29th or around that time only. So we won't be meeting also, but I'm already telling you ahead of schedule that the midterm exam will be having you will be doing these two problems in a computer, in a language, rather than writing some story and all. You will have the midterm question paper will be either Meikawa's algorithm or it will be the Ricard Agarwala, which are more or less the same. Slight differences there. You both, half of you will do one, half of you will do that, and probably I will connect to you live and see what you have done and understand how you have written the code and so on and so forth. That is going to be the plan for the midterm. The Viva, on the other hand, will be the syllabus of primarily the distributed computing, and a little part of the very little part of the first part of the what is that, the parallel computing. I will tell you which part, the fundamental part alone, the basics of distributed computing. So this is the pretty much the plan. So we will you will have the quiz on Monday. That will be the last quiz also. Okay, answer your attendance. Abhilash, Akash, Amit.